Hello and welcome to our next lesson. Today we're going to finish chapter 3. We'll be using the ideas from the last 2 weeks. I showed you how to solve a homogeneous equation with constant coefficients, and I've shown you how to use the method of undetermined coefficients to find a particular solution to a non-homogeneous differential equation. The first section, section 3.8, we will be using and revising these ideas. Section 3.9, the method of variation of parameters. This is a different way to find a particular solution to a non-homogeneous equation. And then finally, in section 3.10, we're going to extend the ideas that we've developed for second order linear equations to higher order linear equations. So first of all, let's do some examples. Let's start with some revision. Let's suppose we have an initial value problem like this. A y double prime plus by prime plus cy is equal to some function g of t with two initial conditions. To solve this problem, the first thing we want to do is we want to solve the homogeneous equation corresponding to our differential equation. Step 2, we need to find a particular solution to our differential equation. To do step 2, in this section we're going to be using the method of undetermined coefficients. The idea is if our function gt does not solve the homogeneous equation, then our ansatz, our guess, should look something like gt. If gt includes an exponential function, then our guess should include an exponential function. If gt is a polynomial, then our guess should be a polynomial, etc. If gt does solve the homogeneous equation, then the idea we saw last week is we take the guess we would have made and then we multiply it by t. And if it still doesn't work, multiply by t again, and so on. Step 3, we're going to take the two functions we found and we're going to add them together. And then finally, we find our constant c1 and c2 to satisfy the initial conditions. It's very important that we do step 4 last. First, we need to find the full general solution to a non-homogeneous equation, and then finally we find the constants. If you try to find the constants too early, then you're probably going to get the wrong answer, which I want to show using this example. Solve y double prime minus y is equal to 2e to the power t with the initial conditions y of 0 is 1, y prime of 0 is equal to 2. I'm going to solve this 2 times. I'm going to do the correct solution, and then I'm going to do a wrong solution by doing step 4 too early. So first, the correct solution. First, we need to solve the homogeneous equation corresponding to our differential equation. In other words, we need to solve y double prime minus y is equal to 0. We know how to solve this. We find the roots, 1 and the minus 1. As soon as we know the roots, we know that the general solution to this homogeneous equation is c1 e to the power t plus c2 e to the power minus t. Step 2, we need to find a particular solution. We go back. Here is the function we're looking at. It's a number 2 multiplied by e to the power t. So we're going to guess that our first guess should be some number multiplied by e to the power t. But This function solves the homogeneous equation, which we've just done. So what we do is we must multiply by t. That means instead of considering a e to the power t, we multiply by t, and our ansatz, our mathematical guess, is going to be a t e to the power t. Differentiate 2 times and then put into the differential equation. We find that 2e to the t must be the same as 2a e to the t. So clearly a is equal to 1, and we found our particular solution, t e to the power t. Step 3, we should add these two functions together. We have the general solution to the homogeneous equation, and then plus our particular solution. So c1 e to the power t plus c2 e to the power minus t, and then plus our particular solution plus t e to the power t. And then finally, step 4, we must find the initial conditions. Differentiate once to get y prime, and then use the initial conditions. Y of 0 is equal to 1, y prime of 0 is equal to 2. Put t equal to 0, we get c1 plus c2 plus 0, and c1 minus c2 plus 1 plus 0. And we find that we must have c1 is 1 and c2 is 0. And that gives us the solution to the initial value problem. Y of t is e to the power t plus t e to the power t. This was the correct solution. Now I'm going to show you the solution gone wrong. This is an incorrect solution because I'm going to do step 4 too early. Step 1 is exactly the same as I did before. This is just copy and paste from before. Now let's suppose after step 1 I do step 4. Suppose I try to find C1 and C2 too early. Remember, this is the correct solution. The correct solution is e to the power t plus t e to the power t. Let's suppose we do this wrong. Let's suppose we try to find C1 and C2 too early. Then y of 0 is 1, which is C1 plus C2. Y prime of 0 is 2, which is C1 minus C2, which implies that C1 is 3 over 2 and C2 is minus a half. So far, we get 3 over 2 e to the power t minus a half e to the power minus t. And then let's suppose after 4, we do step 2. This is a copy and paste from the previous slide. This is exactly what we did before. And then step 3, we add our solutions together. We get 3 over 2 e to the t minus a half e to the minus t plus t e to the power t, which is wrong. This is wrong because the function does not satisfy the initial conditions. It went wrong because I found the constants C1 and C2 too early. This is the correct solution at the top. And this solution is wrong. Let's do, I think, a more complicated example. This is a question which I asked in an exam in 2013 in a slightly different course. And in 2013, I gave students 2 hours to solve 4 questions. So really, they had 30 minutes to solve this question. Solve minus y double prime plus 6y prime minus 16y is equal to 1 plus 6 e to the power 3t sine 2t with the initial conditions. Y of 0 is 15 over 16. Y prime of 0 is equal to minus 1. So what we're going to do. First, we're going to look at the homogeneous equation. First, we're going to look at minus y double prime plus 6y prime minus 16y is equal to 0. Here we go. We write down the characteristic equation, minus r squared plus 6r minus 16 is equal to 0. And we find the roots, which in this case are 3 plus or minus I square root of 7. As soon as we know the roots, we know the general solution to the homogeneous equation is this function written in green. We'll come back to this later. Now, next, instead of looking at the whole non-homogeneous equation, I'm going to break this up into some easier pieces. First, I'm going to look at minus y double prime plus 6y prime minus 16y is equal to 1. I'm going to go back a couple of slides. Here we go. Forget the initial conditions for now. Forget the plus 6e to the 3t sine 2t for now. I just want to look at this equation with equal to 1 on. After this, I'm going to forget the 1 and I'm going to look at the differential equation with 6e to the 3t sine 2t separately, and then I'm going to add my functions together. So, where was I? Next, consider minus y double prime plus 16y prime plus 16y is equal to 1. Look at the function. The function 1 is just a number, so my ansatz is just going to be a number. And I calculate that 1 is minus 16c, hence capital Y must be minus 1 over 16. Next, another small part of the problem. Minus y double prime plus 6y prime minus 16y is equal to 6e to the power 3t sine 2t. If you wanted to, you could do the previous step and this step at the same time, but I think it's easier if we break it up into lots of easy problems. We don't have to worry about this function satisfying not the homogeneous equation, because that doesn't have cos 2t or sine 2t in it. So we're going to try the ansatz a e to the 3t cos 2t plus b e to the 3t sine 2t. You will remember that anytime we have either sine or cos, we must have the other one as well. This is the calculation. I'm not going to dwell on this. You can check this later. We find that for this to be true, we must have that a is 0 and b is equal to minus 2. So we found a particular solution, minus 2e to the 3t sine 2t. To find the general solution to the non-homogeneous differential equation, we add these three functions together. In green, I had the general solution to the homogeneous equation. That's the equation with equal to 0. The orange bit was the equation with equal to 1. And then this blue part of the function was the last one that we did. Add these functions together, we have the general solution to the non-homogeneous equation. And the final step, step 4, the one we always need to do last, is we need to find the constants C1 and C2 to satisfy the initial conditions. Again, I'm not going to dwell on the calculation. You can go through this and you can check that C1 must be 0 and C2 must be equal to 1. And then we can write down the solution to the initial value problem. If I gave you a question like this in your midterm exam, I will expect you to be able to solve this problem within 30 minutes. Before the exam, go through this, practice with the homework questions, or practice with the exercises in the lecture notes, and check that you could solve a problem like this in less than 30 minutes. Now, this method, the method of undetermined coefficients to find a particular solution, this works well as long as the function gt is what I'm calling a nice function. There's a typo here. This should be e to the power kt. I'll fix that later. E to the power kt, sine kt, a polynomial, an exponential multiplied by hyperbolic function, say. These are all functions I'm calling nice functions. We can differentiate them and we get roughly the same type of function. However, if our function gt is a less nice function, then we're going to need a different method to find a particular solution. And I'm going to show you another method now to find a particular solution. This is the method of variation of parameters. In the last section, I was deliberately quick, skipping the details, leaving that for you to check later. For this section, I'm going to slow down. For example, find a particular solution to y double prime plus 4y is equal to 3 cosec t. And this is a function which I say is not a nice function, because when we differentiate it, we don't get the same type of function. Let me tell you the idea behind this method. We know the general solution to the homogeneous equation is c1 cos 2t plus c2 sine 2t. So the idea in this method is, instead of constant c1 and c2, we're going to guess that a particular solution has functions here. Some function u1t cos 2t plus some function u2t sine 2t. And then we're going to aim to find u1 and u2. When we do this, when we try to find u1 and u2, we will find that there are infinitely many functions that we could use if we wanted to. We only need to find one pair of functions. We don't need to find every single u1 and u2. So that gives us some freedom. We're going to be allowed to introduce an extra condition just to make our calculation easier. As long as we can find one pair of u1 and u2 which works, that's good enough. And whatever we do to make our calculation easier, that would be okay. So we're going to start by supposing that our particular solution is a function u1 cos 2t plus a function u2 sine 2t. And differentiating this, already it starts to look complicated. We have 4 terms here, and I want to make this easier. It's already getting complicated, so on the previous slide I said we have the freedom to introduce an extra condition whenever we want. I'm going to introduce a condition here. I'm going to assume that these terms in red are equal to 0. This is my one chance to introduce an extra condition. I'm using it here. So that makes y prime easier. And then y double prime has only 4 terms instead of lots of terms. Then put these into the differential equation. Free cosec t should be equal to y double prime plus 4y. Using the formula from the previous slide, this is equal to minus 2 u1 prime sine 2t plus 2 u2 prime cos 2t. Now we have two equations for u1 and u2. We have this green equation which we've just found. u1 and u2 must satisfy the green equation, but u1 and u2 must also satisfy this red equation that I introduced, this extra condition that I invented to make the calculation easier. If we can find u1 and u2 which satisfy this system of equations, then we can find our particular solution. I've repeated this system. From the second equation, the latter condition, we can rearrange this to u2 prime is minus u1 prime, cos 2t over sine 2t, and then we can put this into the former equation, the first equation. Rearranging the first condition, so putting this formula into the second condition, we get this one. Multiply everything by sine 2t, an extra sine 2t on the left. Sine 2t becomes sine squared 2t. Multiply by sine 2t, this cancels, and we are left with minus 2 u1 prime cos squared 2t. We know what sine squared plus cos squared is. We know that sine squared plus cos squared is equal to 1. So on the right side, we just have minus 2 u1 prime. Divide both sides by minus 2. And we find a formula for u1 prime. u1 prime must be minus 3 cos t. After we know u1 prime, we can put that into the top formula in the orange box, and we can calculate that u2 prime is 3 over 2 cosec t minus 3 sine t. This slide has just been algebra. We've just been using linear algebra to solve a linear system of two equations. After we know u1 prime and u2 prime, we can integrate to find u1 and u2. Of course, u1 is the integral of u1 prime. That is the integral of minus 3 cos t, which we know is minus 3 sine t. And likewise, u2 is the integral of u2 prime. And when we calculate this, we get 3 over 2 natural logarithm of the absolute value of cosec t minus cos tan t plus 3 cos t. And then we're ready to write down the particular solution. Remember that we started with the particular solution u1 cos 2t plus u2 sine 2t. Now we know u1 and we know u2. Put these in and simplify, and we find our particular solution, which you can see is 3 sine t plus 3 over 2 natural logarithm of the absolute value of cosec t minus cotan t multiplied by sine 2t. Complicated function. Yes, our function was too complicated to use the method of undetermined coefficients, so we needed this more advanced method. Let me give a summary of this method, because I'm aware that first time you see this, this looks complicated. Suppose we know the general solution to a homogeneous equation. And suppose that we want to find a particular solution to the non-homogeneous equation. We guess that our particular solution looks like the general solution to the homogeneous equation, but instead of constants c1 and c2, we guess that we have functions u1 and u2. To stop our calculation getting too complicated, we make an extra condition, and it's always the same extra condition. We always assume that u1 prime y1 plus u2 prime y2 is equal to 0. We differentiate capital Y and we put it into L of y is equal to gt, and we find equations for u1 prime and u2 prime. After we know u1 prime and u2 prime, we can integrate to find u1 and u2, and then we know a particular solution to the non-homogeneous equation. Two things to remember for the method of variation of parameters. We always start with u1 y1 plus u2 y2, and we always make the extra condition that u1 prime y1 plus u2 prime y2 is equal to 0. And then after that, it's playing with the equations to find u1 and u2. Another example. Find a particular solution to y double prime plus 2y prime plus y is equal to e to the t ln t. E to the t is a nice function. If we just had e to the t, then we would probably use the method of undetermined coefficients. But we also have an ln t, and ln t is not a nice function. When we differentiate ln t, we don't get ln t. So we must use the method of variation of parameters. First, we need the general solution of the homogeneous equation. You know how to do this. You can find that the general solution of the homogeneous equation must be c1 e to the power t plus c2 t e to the power t. Now we're ready to do the method of variation of parameters. We replace c1 and c2 by functions. We're going to guess that the particular solution, capital Y, is u1t e to the t plus u2t t e to the power t. Then we introduce our extra condition. The extra condition, as I said previously, we always want u1 prime y1 plus u2 prime y2 is equal to 0. This is the formula we remember. This is the equation we always use. And for this example, That means that u1 prime e to the power t plus u2 prime t e to the power t is 0. But because e to the power t is always non-zero, for this example, our extra condition becomes u1 prime plus u2 prime t is equal to 0. We will need this formula later. So, next we need to differentiate y prime 2 times. Y prime, y double prime, and then I'm going to put them into the differential equation to find another condition for u1 and u2. u1 prime is u1, so capital Y prime is u1 prime e to the t plus u1 e to the t plus u2 prime t e to the power t plus u2 e to the t plus u2 t e to the power t. We made the extra condition that these two terms with the line through must be equal to 0, so we can cross them out. u1 prime must be u1 e to the t plus u2 e to the t plus u2 t e to the power t. And then we differentiate again. You can check later this is correct. And again, we have two terms that we can cancel using our extra condition. And we get y double prime is u1 e to the t plus u2 prime e to the power t plus 2u2 e to the power t plus u2 t e to the power t. Put these into the differential equation and then simplify. All of the u1 terms should cancel out. The u2 terms should cancel out. We might get some u1 prime terms and we might get some u2 prime terms. For this example, we get just a u2 prime term. E to the power t, L, and t must be equal to u2 prime e to the power t. We could cancel the e to the power t's out, and we find that u2 prime must be ln t. Great. u2 prime must be ln t. Using the extra condition from the previous page, we know that u1 prime is equal to minus u2 prime t. So u1 prime must be minus t ln t. Then we've done most of the hard work. After we integrate these two functions, we will know u1 and u2. After we know u1 and u2, we can write down the particular solution. So integrate these two functions. Recall your calculus 2 theory on how to integrate ln t or t ln t. You can check that u1 must be minus a half t squared ln t plus a quarter t squared, and u2 must be t ln t minus t. And then we can write down the particular solution. The particular solution must be u1 e to the power t plus u2 t e to the power t. Now we know u1 and we know u2. We can substitute these in and we can find that the answer to this example is a half ln t minus 3/4, all multiplied by t squared e to the power t. And this is the idea behind the method of variation of parameters. That's the theory, that's how it works, but you're probably asking yourself, isn't there an easier way to do this? And the answer is yes. We have a theorem with a nice formula. First of all, suppose we know that y1 and y2 form a fundamental set of solutions to the homogeneous equation y prime plus pt y prime plus qt y is equal to 0. Then we have a nice formula for a particular solution to the non-homogeneous equation. Same left-hand side, but now equal to gt. And the formula is, the particular solution is minus y1 multiplied by the integral of y2g divided by w plus y2 multiplied by the integral of y1g divided by w, where w is the Wronskian of y1 and y2. Now this is basically the same as what we've been doing. In the previous two examples, we found u1 prime and u2 prime. We integrated these two functions, and then we wrote down u1 y1 plus u2 y2. Or to say this another way, we wrote down y1 multiplied by the integral of u prime plus y2 integral of u2. And that's basically what we have here. y1g divided by w is going to be the same as y2 prime, minus y2g over w is the same as y1 prime. Using this formula will be exactly the same as the previous method. We're still going to have to do the two integrals, which may be easy or may be difficult, and then we put them in. For example, find a particular solution to y double prime minus 2y prime plus y is equal to e to the power t ln t. We've just done this example. We know the answer. Now we're going to use the theorem to solve this. Step one. First, we need to know a fundamental set of solutions to the homogeneous equation corresponding to the differential equation. And it's straightforward to find that fundamental set of solutions is e to the power t, e to the power t. We know this because we did this in the previous example. We also need the Wronskian of y1 and y2. The Wronskian is the determinant of the 2 by 2 matrix y1, y2, y1 prime, y2 prime. Determinant e to the power t plus t. And when we calculate this, we get e to t. Let me repeat what we have at the top. y1 is e to the power t e to the power t. Our function g on the right-hand side of the differential equation was e to the power t ln t, and the Wronskian of y1 and y we've just found is e to the power t. We can take these functions and we can put them into the equation from the. So here we go. Capital Y must be minus e to the power t, integral of t e to the power t, e to the power t ln t, divided by e to the power 2t. Straight away we can see some of these terms are going to cancel. We have e to the 2t on the top and e to the 2t on the bottom. And then second term, t e to the power t, integral of e to the power t, e to the power t, ln t, divided by e to the power 2. And again, look, some of these terms are going to cancel. E to the power 2t on the top, e to the power 2t on the bottom. We are left minus e to the power t, integral of t ln t, dt plus t e to the power t, integral of ln dt. Getting the point is easier if we use this, but we still have to do the exact two integrals previous. Here we go. Calculate these integrals and then simplify. We find that a particular solution is a half ln t minus 3/4, all multiplied by t squared power t, which is exactly the same answer that we found. Our final topic for today is higher linear differential equations. I'm getting some warnings on my bad connection. Type in the chat if you can. In final section, we're going to then the ideas that we've developed for second order linear to higher orders. For example, let's suppose I want to solve this homogeneous fourth order linear differential equation. 4 derivatives of y plus y triple prime minus 7y double prime minus y prime plus 6y is equal to 0. With these initial conditions. This is a fourth order equation, so we need to have 4 initial conditions. First thing we do is we write down the characteristic equation of the differential equation. R to the power 4 plus r cubed minus 7r squared minus r plus 6 is equal to 0. And if we can solve this equation, we can find that the roots are 1, minus 1, 2, and minus 3. You can guess what we do next. We can write down that the general solution to the differential equation. First of all, we have r1 is 1, so we can have an e to the power t term. We have r2 is minus 1, so we can have an e to the power minus t term. We have r3 is equal to 2, so there should be an e to the power 2t. And we have r4 is minus 3, So we expect to have an e to the power minus 3t term. And in fact, this is true. The general solution to the differential equation is c1 e to the power t plus c2 e to the power minus t plus c3 e to the power 2t plus c4 e to the minus 3t. Exactly the same ideas that we used for second order equations, but now we have 4 functions in our fundamental set of solutions instead of only 2. The number of functions in our fundamental set of solutions must always be the same as the order of the differential equation. Then, to solve the initial value problem, we need to find the constant C1, C2, C3, and C4. There's another typo just here. This should be C subscript 4. You know how to solve linear systems like this. You could solve this and you could find that C1 must be 11 over 8, C2 must be 5 over 12, C3 must be minus 2 over 3, and C4 must be minus 1 over 8. Then we can write down the solution to the initial value problem. 11 over 8 e to the power t plus 5 over 12 e to the power minus t minus 2 over 3 e to the power 2t minus 1 over 8 e to the power minus 3t. Same ideas that we would use for second order equations. We might also solve a non-homogeneous fourth order linear equation. Solve 4 derivatives of y minus y is equal to e to the power t. We start by finding the general solution of the homogeneous equation by using the characteristic equation. The roots are 1, minus 1i, and minus I. So the general solution to homogeneous equation must be c1 e to the power t plus c2 e to the power minus t plus c3 cos t plus c4 sin t. Next, we use the method of undetermined coefficients to find a particular solution to the non-homogeneous equation. Now, before I go on, you will note that e to the power t appears inside the general solution to the homogeneous equation. That means we can't use e to the power t in our ansatz. We need to multiply by t and consider t e to the power t. Since e to the power t solves the homogeneous equation, we're going to try the ansatz, some constant capital A t e to the power t. Differentiate 4 times, put them into the differential equation, and we can find that A must be a quarter. This is exactly the same ideas that we developed last week. Therefore, a quarter t e to the power t is a particular solution to the differential equation, and therefore the general solution to the differential equation is the general solution to the homogeneous equation and then plus a quarter t e to the power t. Remember what we did for second order equations when we had repeated roots? We just multiplied by t. And we can use the same idea here. Let's suppose we have some differential equation, and let's suppose that the roots are 7, 7, 7, 7, 7, and 8. Then we can write down the general solution. First, of course, we have C1 e to the power 70. Okay, this is what we expect. The second root is repeated, so we multiply by t. C2t e to the power 70. But then the third root is also 7. So again, we multiply by t. C3t squared e to the power 70. And then fourth root is also 7, multiplied by t. Fifth root is 7, again multiplied by t. And then the sixth root is 8, so just c6 e to the power 8t. We might also go backwards in the final example for today. Let's suppose I tell you a solution of a differential equation, and I ask you to find a differential equation which has this general solution. You will find questions like this in the exercise, in the lecture notes for you to practice. Now let's look, what do we have here? Start with C1 e to the power t. So that tells us the first root is equal to 1. Then we have C2t e to the power t. Second root must also be equal to 1. Then we have C3 e to the power 2t sine t plus C4 e to the power 2t cos t. This tells us R3 and R4. Let me write this again. Must be 2 plus minus I. And then look at the last two terms. C5 e to the power 2t t sine t plus C6 e to the power 2t t cos t. From this we find R5 and R6 again must be 2 plus or minus I. So let me type this. The first two terms corresponding to a double repeated root R is equal to 1. And the last four terms correspond to a double complex root 2 plus or minus I. That means that the characteristic equation must look like this. R minus 1 squared, first of all, because we have root R is equal to 1 twice, we have two of them. And then we have 2 plus I, and we have 2 minus I. And each one is repeated twice, so we have the squared here. Multiply this out, and we have our characteristic equation. R to the power 6 minus 10 r to the power 5 plus 43 r to the power 4 minus 100 r cubed plus 131 r squared minus 90 r plus 25. As soon as we know the characteristic equation, we can write down a differential equation which has this characteristic equation. Instead of R6, 6 derivatives of y. Instead of minus 10 r to the power 5, minus 10 and then 5 derivatives of y, and etc. Final term, instead of plus 25, we have plus 25y, and then equal to 0. If I give you the general solution to a homogeneous linear differential equation, you can write down the characteristic equation, and then from the characteristic equation, you can write down a differential equation. And this is the end of today's lesson. This is the end of chapter 3. We still need to talk about the Laplace transform, and we need to talk about systems of differential equations. Next week, we're going to cover the definition of the Laplace transform, and then we're going to use the Laplace transform to solve some initial value problems. If you have any questions, you can type them in the chat now.